The first book I want to cover today is this one, Breeden, Topology and Geometry. And the book is a quite high-level, very quick overview of a lot of topics on pointed topology, algebraic topology, and differential topology and geometry. So we start with general topology, and you see it goes quite deep and quite fast. It does nets, compactness, paracompact, quotient spaces, even bare category theorem. Then it goes differential manifolds, where it goes and basically does a lot very quickly. Tangent bundles, tubular neighborhoods, Lie groups, transversality. Then it does the fundamental group, homology theory, cohomology, products and duality, homotopy theory, and then some appendices. So the book is quite fast. It goes quite quickly. So I mean, Mirror might be interested in this book, but Lie is far more gentle and much more careful about notation. This book is, I guess, too quickly if it really is your very first book on a topic. But overall, the book is pretty good. It's pretty solid. It's for quite a famous book, whatever that means. But yeah, I didn't work through it completely myself, but I did like what I saw. It just it's very fast paced. That's to say the least. So yeah. Next we have this book here by Trèves, François Trèves, Topological Vector Spaces, Distributions and Kernels. And this is basically a book on function analysis, but very foundational. So it means topological vector spaces. So part one is on basically everything you want to know about topological vector spaces. Colloquially convex spaces, Hilbert spaces, normable spaces, LF spaces. Then it goes to duality, a very general form of Hahn-Banach theorem, radon measures, and so on. And then it does tensor products and kernels. So if you're interested in this material, this book is good, but I'm definitely not too interested in this material anymore. I think topological vector spaces are kind of dry, are kind of rather boring theory. Not very fun. I think function analysis is way more fun once you get Banach or Hilbert spaces, while something like topological vector spaces is probably not so interesting, at least not to me. It is interesting. You would be interested in topological vector spaces and locally convex spaces. If you want to do distributions or generalized functions, then you would want them eventually. And this is also what the book kind of works towards. But yeah, I would basically just do it from a generalized function book. But yeah, if you are interested in topological vector spaces, this book is the main source on the topic. It does contain everything you want. Then we have two books by Bourbaki. General Topology chapters 1 and 4, and General Topology chapters 5 to 10. Basically, I needed this for my thesis because this book contains a lot of stuff on topology that other books do not contain. And this book contains very specialized stuff very rigorously that other books do not contain. So we see it says chapter 1, topological structures, where they deal with open sets, continuous functions, basically everything, filters, limits, very general, proper mappings, connectedness, very general. Then it does uniform structures, uniform spaces, uniformly complete spaces. Then it does topological groups, topologies on groups, subgroups, uniform structures on groups, and so on. Then it goes on to do the real numbers, definition of real numbers, uniformity on real numbers, real valued functions, and so on. Then we have chapter 2, the next volume. It starts with one parameter groups, topological characterization, exponential logarithms, real number spaces and projective spaces. The additive group Rn, and then we have complex numbers, use of real numbers in general topology, metroidable groups, normal spaces, and so on. And then function spaces, and that's basically it. So what do I think of Bourbaki? I think Bourbaki was a waste of time. I really don't like the books. They're, for a beginner, they're far too dry. As a reference topic, I'm not sure who's interested in them by now. I think there are much better books on the topic. I appreciate them in the history. They fixed a lot of notation. They did a lot of good stuff in the history of things. But I would never recommend anybody Bourbaki at this point anymore. It is definitely not my style of math. I mean with that, the math that really bases everything, just tries to make everything as general as possible, basically general as abstract as possible. I don't vibe with that anymore. Maybe I did in the past, but not anymore. But yeah, this is the Bourbaki topology books, which I needed at some point. I have some others too, but you'll see them later. Alright, next a book I actually really like a lot, and I hope Martin is going to do this book with me very soon. And it is this one, Topology and Groupoids by Ronald Brown. It has some very beautiful stuff. So it starts with topology on the real line, starts very easy. Then it has topological spaces. Then we have connected spaces and compact spaces, identification spaces and cell complexes, projective and other spaces, the fundamental groupoids, not the fundamental group, but fundamental groupoids, cofibrations, some combinatorial groupoid theory, computation of the fundamental groupoids, covering spaces, covering groupoids, and orbit spaces and orbit groupoids. So what are some? So this is a very non-standard point of view of algebraic topology, where algebraic topology and especially homotopy theory is interested in fundamental groups. This generalizes that pursuit to the fundamental groupoids. Why do we generalize it? Why do we bother? Because it happens that a lot of theorems become simpler and nicer when we deal with the fundamental groupoids. I'm thinking of the Van Kampen theorem. Van Kampen theorem is a theorem that holds very cleanly in the first fundamental group, but not so much for the next ones. It is the fundamental groupoid which really does these things a lot better. So, yeah, for somebody interested in algebraic topology, highly recommend this book. This book has excellent exercise, has excellent delivery. It is a very beautiful book, and I think I really like this one a lot. I think it is an excellent successor to Lee, or, well, Lee's topology book, or any algebraic topology book. I think I really like this book a lot. It's very pretty. Another book on topology. Here we have Topological Groups by Mark Lee. So the table of contents is the following. It starts with groups and topologies, linear space and algebras, subgroups of Rn, matrix groups, connectedness of topological groups, metric groups of functions, compact groups, and character groups. So a treatise basically on groups, topological groups, and topologies on groups and everything to do with them. Very well written book, solid book. I think for beginners this might be my favorite book on the topic. It's just too bad it doesn't really go too much into harmonic analysis. It does a bit, of course, as it must do, but it strays very much on the topological side. Then we have a shit book, this shitty thing, Hatcher, Algebraic Topology. Hate this book. It's so recommended all over the place. Everybody recommends this book nowadays. I really don't like it. So it's chapter 1 is the fundamental group. Then we go to homology, cohomology, and then finally homotopy theory. I really don't like the writing. I don't like how non-rigorous this book is, how basically you have to see everything without really doing it formally. I get algebraic topology is not a formal field in the sense that you can't really describe things formally most of the time, but come on, I mean, the guy goes too far. The exercises are just, I mean, even the very first chapter is like boring as hell with very difficult exercises. I mean, I don't know why he wrote it like this. I don't get it. I don't get it at all. Another book on algebraic topology by Rothman, Introduction to Algebraic Topology. This is the same Rothman as Krim's algebra book. So it starts with introduction, some basic topological notion, simplexes, the fundamental group, singular homology, long exact sequences, excision and applications, simplicial complexes, CW complexes, natural transformations, covering spaces, homotopy groups, and cohomology. Yeah, solid book, of course, but I guess there are a bit better books on the topic right now. I went through a good part of this and basically just got a bit bored. The writing style is like an old book. It's not especially engaging. It's not that it really grabs your attention and yeah, makes you love this field. It just basically is everything you want, and let's keep it at that. Next, a very niche book, James, Fiberwise Topology. Basically tries to do topology with the fibers, and the fibers are inverse elements of inverse mappings of elements. So we have Fiberwise topology, Fiberwise uniform spaces, Fiberwise homotopy theory, and some miscellaneous topics. So yeah, I'm interested, if you're interested in the foundation of topology and some niche approaches, then you will love this book, but I'm not sure who I know that would be interested in this. But yeah, I do like this approach just because I'm interested in these kind of things. Next we have a book by Coxeter, another book by Coxeter. The book is Non-Euclidean Geometry by Coxeter. Coxeter, of course, a famous geometry writer. So it starts with historical development, it starts with real projective geometry foundations, polarities, conics, and quadrics. It does homogeneous coordinates, elliptic geometry in 1 dimension, elliptic geometry in 2 dimensions, elliptic geometry in 3 dimensions, descriptive geometry, Euclidean and hyperbolic geometry. Then hyperbolic geometry in 2 dimensions, circles and triangles, the use of a general triangle of reference area, Euclidean models, and concluding remarks. Coxeter, of course, very famous writer. I think I have all his books. They're all really good, but they're very old style. Nobody does geometry like this anymore, sadly. So yeah, if you're interested in this kind of stuff, Coxeter definitely is the person you want. But I'm not sure. I'm not sure there are many people out there anymore, aside from me, who really like this kind of old style stuff anymore. People have all moved on to algebraic geometry stuff and that kind of stuff. So yeah.